Hi guys, welcome to this video where we're going to take a look at a problem that I found in this book, Challenging Problems in Algebra by Alfred, Posamentier and Charles Salkind. The problem is in chapter 17, problem 27, which says the sum of a number and its reciprocal is 1. Find the sum of the nth power of the number and the nth power of the reciprocal. So if I wanted to write this out in symbols, it would look something like the following. If we assume that x is the number that we're interested in, so we have x plus 1 over x, a number plus its reciprocal is equal to 1. We're interested in the value then of the nth power of x plus the nth power of the reciprocal. Now, because 1 over x to the power of n, the nth power of the reciprocal, is equal to the reciprocal of the nth power of x, I'm going to write this as 1 over x to the power of n instead. So we've got a problem that's equivalent to the one in the book, but symbolically it's slightly different. But it doesn't make any difference. So initially when I read this problem, I had a feeling that x was not going to be a real number. X is not going to be a real number. And I'll explain why. So because we know that x plus 1 over x is equal to 1, and if a number is positive, then its reciprocal is going to be positive. If a number is negative, its reciprocal is going to be negative. So if x were to be negative, its reciprocal would be negative, and therefore the sum would also be negative. It couldn't be equal to 1. So x must be positive. Obviously, x can't be 0 because we can't talk about the reciprocal of 0. So x must be positive if it's a real number, that is, if it's a real number, and we'll find out in a second that it's not. But let's assume that it is. Then if x is equal to 1, 1 over x is also equal to 1, and therefore the sum of the number and its reciprocal would be equal to 2, which conflicts with this information here. If x is greater than 1, then its reciprocal is going to be between 0 and 1, and therefore the sum of the number and its reciprocal is going to be greater than 1 by virtue of the fact that x is greater than 1. If 0 is less than x is less than 1, then the reciprocal 1 over x is going to be greater than 1, and again x plus 1 over x would be greater than 1. So all of the positive real numbers are kind of ruled out here as possibilities because they all conflict with this equality here. So the upshot is that x can't be a real number. So what does that mean? It means that x is probably going to be a complex number. Possibly an imaginary number, but most likely a complex number. So initially I didn't really have any ideas, and this is normal when it comes to solving problems. I didn't really have any definite ideas about what exactly I wanted to do to solve this problem. So I thought, well, let's try and actually find the values, the possible values of x. This might be useful, it might not be useful, but it's something that I can do, just see where it goes. So that's what I did. And therefore, going back up to this equation, multiply through by x, there's no risk that x is going to be equal to 0 or anything like that. So I can multiply through by x to give the quadratic equation x squared, and with a bit of rearrangement as well, x squared minus x plus 1 equals 0. And the solutions to this quadratic equation are going to be x equals half plus I root 3 over 2, or x is equal to a half minus I root 3 over 2, where I is, of course, equal to the square root of minus 1. So we've got two possible values for x, but it turns out that if x is equal to this, half plus I root 3 over 2, then a half minus I root 3 over 2 is 1 over x, and vice versa. If I'd set x equal to a half minus I root 3 over 2, 1 over x would be equal to this. So for the sake of argument, we can just take x to be equal to a half plus I root 3 over 2 without loss of generality. I don't need to consider both possibilities. So I'm going to take this as my value of x. And at this point, I kind of stopped with this line of reasoning. I didn't think that this was going to go anywhere. I actually had another idea that I wanted to try out, but it turns out that this is actually quite useful. The idea that I did have another idea about what I could do with this, but that'll come into play later. It involves the trigonometric form of this number. So I'm going to put that to one side for a second. We are going to be using that x equals a half plus I root 3 over 2 at some point, but we're just going to leave it to one side for now. So my other idea that I wanted to pursue was the following. So if we start with x plus 1 over x equals 1, then what we get is that if we square this, x plus 1 over x squared, this is of course equal to 1 squared equal to 1. Expand this out, I get x squared plus 2 plus 1 over x squared. And therefore, x squared plus 1 over x squared is equal to 1 minus 2 minus 1. Okay. So then I decided to move on to x cubed plus 1 over x cubed. So how do I do that? X squared plus 1 over x squared times x plus 1 over x. Well, this is just equal to 1. This is equal to minus 1. So the product is going to be equal to minus 1. And now if I expand this out, I get x cubed plus x plus 1 over x plus 1 over x cubed. This, of course, is just equal to 1. And therefore, x cubed plus 1 over x cubed is going to be equal to minus 1 minus 2. Okay, so then I thought this is getting a bit tedious. I don't really want to move on to x to the power of 4. I'm going to go straight for x to the power of n, if I can. So what I did then was I tried x to the power of n plus 1 over x to the power of n times x plus 1 over x. Actually, I ended up with x to the power of n plus 1, but it doesn't make any difference. So this is equal to 1. We'll sort that out in a second, the value of this. So expand this out, I get x to the power of n plus 1 plus x to the power of n minus 1 plus 1 over x to the power of n minus 1 plus 1 over x to the power of n plus 1. And therefore, because that's equal to 1, I get that x to the power of n plus 1 plus 1 over x to the power of n plus 1 is equal to x to the power of n plus 1 over x to the power of n minus x to the power of n minus 1 plus 1 over x to the power of n minus 1. So I get a kind of recurrence relation here. If I want to find out what the value of x to the power of n plus 1 over x to the power of n is, I just do the previous value minus the value 2 less than n. In this case, n plus 1. Okay, so let's say I want to figure out x to the power of 4 plus 1 over x to the power of 4. This is going to be x cubed plus 1 over x cubed, or the value of x cubed plus 1 over x cubed, which is minus 2, minus the value of x to the power of x squared plus 1 over x squared, which is minus 1. Minus 2 minus minus 1 is minus 1. X to the power of 5 plus 1 over x to the power of 5 is equal to the value of x to the power of 4 plus 1 over x to the power of 4 minus 1 minus the value of x cubed plus 1 over x cubed minus 2, which gives me 1. So here I'm getting a series of values. So if we've got n equals 1, we get the value 1. When n equals 2, we get the value minus 1. When n equals 3, we get the value minus 2. n equals 4, we get the value minus 1. n equals 5, we get the value 1. And we can continue this. N equals 6, we'd get the value 2. N equals 7, we'd get the value 1. N equals 8, we'd get the value minus 1. So what happens is the values kind of cycle, they cycle through. 1, minus 1, minus 2, minus 1, 1, 2, 1, minus 1. So when we get here, we kind of start off again. And we cycle through the values all over again. So this is fine. We could, in theory, I guess, figure out some general expressions for, we'd have to maybe look at different cases to find the value of n for values of n of this form and values of n of that form. It's going to be a bit of a pain, to be honest with you. So this is fine. It gives some insight into the problem, but it doesn't quite solve the problem to my satisfaction. And it was at this point that I thought, maybe I can make some more use of this complex number. So we'll keep these in mind, these values, but now we're going to go back to this complex number. And what I'm going to do is I'm going to write this complex number in its trigonometric form. So we get x is equal to cos pi by 3 plus I sine pi by 3. Because I know that cos pi by 3 is a half and sine pi by 3 is root 3 over 2. So pi by 3 is radians, pi by 3 radians, which is equivalent to 60 degrees if you're not familiar with radians. I will be working with radians though. And it turns out therefore that 1 over x is equal to cos pi by 3 minus I sine pi by 3. And now we can use De Moivre's theorem. So De Moivre's theorem says that cos theta plus I sine theta to the power of n, where n is an integer in this case, is equal to cos n theta plus I sine n theta. So x to the power of n is going to be equal to cos n pi by 3 plus I sine n pi by 3. X to the power, 1 over x to the power of n is going to be cos n pi by 3 minus I sine n pi by 3. And interestingly, when I add the left-hand sides here and the right-hand sides, what I get is that x to the power of n plus 1 over x to the power of n is equal to twice cos n pi by 3. So this is the value that we're looking for, the value of the nth power of x and the nth power of the reciprocal. So we can check this against the values that we got before using the elaborate method that I went through before. So in n equals 1, we get that we get 2 cos pi by 3. Cos pi by 3 is a half. 2 times a half is 1. When n equals 2, we get 2 cos 2 pi by 3. Cos 2 pi by 3 is minus a half. So 2 times minus a half, minus 1. N equals 3. So let's just think about the cos graph, by the way. So the cos graph looks something like this. That's pi by 2. This is pi. 3 pi by 2, and so on, minus 1, 1. When n equals 3, we get 2 cos 3 pi by 3, or 2 cos pi. Cos pi is minus 1, so it's going to be minus 2. N equals 4, 2 cos 4 pi by 3. 4 pi by 3 is about here, so that's going to give, what, minus a half. The graph's not drawn very well, but it's going to be minus a half. 2 times minus a half is minus 1. N equals 5. 5 pi by 3 is going to be over here somewhere. It's going to be plus a half. So we get 2 times a half, which is 1. And we can see that we're getting exactly the same values as we did before. But rather than having them written out as a list for each value of n, and just kind of seeing this cyclical pattern, 1 minus 1 minus 2 minus 1, and so on, we get it in a nice succinct formula here. So the sum of the nth power of x and the nth power of the reciprocal of x is equal to 2 cos n pi by 3, and that solves the problem.